So here's a picture of a field effect transistor, at least how we draw it in a circuit. We use this symbol. The direction of the arrow has significance here. In this case, we have an N-channel FET. There are also such things as P-channel FETs and so on. And sometimes you see more complicated diagrams indicating specifics about how the materials are arranged. Those details are not important at the level that we're going to address design, although they certainly do have bearing on advanced design problems. So for now, we'll just stick to N-channel FETs, and we'll talk about how these are going to work. In most cases, this detail will not come into play. In any event, we also have three terminals like we did for the BJT. In place of the collector, we have the drain. In place of the emitter, we have the source. And in place of the base, we have the gate, with a change in the letters used to identify these things, as you would expect. Just as in the BJT, we define the current in the drain to be into the transistor, the current at the gate to be into the transistor, and the current at the source to be out of the transistor. A thing to know about field effect transistors, and one of the things that makes them very useful, is that the gate current is usually, not always, but usually negligible. And the defining relationship is that the drain current is given by some constant, which depends on the particular transistor, that's I sub DSS, times this factor, 1 minus the gate source voltage, that's the voltage here, divided by this thing, which is the pinch-off voltage, which depends on the transistor, and this quantity is squared. So I pointed out that the BJT is essentially a current-controlled current source. Well, the FET is essentially a voltage-controlled current source. Here's the controlling voltage, and here's the resulting current. FETs used as amplifiers, typically in the common source configuration, with the drain as the output and the gate as the input. In the N-channel enhancement mode, the gate source voltage has to be greater than 0 for this to work as an amplifier. And in that case, the biasing of this device is very, very similar to what we do for bipolar junction transistors. However, that's not the only possibility. Some N and P channel depletion mode devices, well, they also have VGS greater than 0 to work as amplifiers. But otherwise, VGS has to be less than 0. So some FET amplifiers work as amplifiers when the gate source voltage is less than 0. That's only a minor complication, but it does affect the way bias networks get designed. Now, the common source configuration, in which FET amplifiers are often but not always used. Very analogous to the common emitter configuration for bipolar transistors. That is, the gate is the input and the drain is the output. The main difference is that a FET has very, very high input impedance, which makes these things great for buffering. A buffer is an amplifier which is insensitive to its input impedance. So a buffer is something that you would add to a circuit when you have a problem in that the input or the source impedance is either unusual or variable. And when you have either one of those things, it's useful to have an amplifier which is not sensitive to that value. And a FET certainly falls in that category because it has very high input impedance. It's just not that sensitive to what input impedance you apply to it. For a FET amplifier, biasing consists of choosing the drain current and the drain source voltage. This is analogous to the BJT, where what we choose is I sub C, the collector current, and V sub CE, the collector emitter voltage. But again, certainly not the only way to go. Common gate is sometimes employed for low gain LNAs, for example. Common drain, sometimes known as a source follower, is often employed for active antennas. Okay, now FETs versus bipolars. How do we choose between these things? Well, FET transistors tend to dominate in RF applications above 4 gigahertz for the reasons I mentioned previously in terms of the weaknesses of the BJT. FETs are typically the only way to go above 10 gigahertz or so. Now, this is a very general statement. I'm sure there are bipolar transistors that work very well in applications above 10 gigahertz or so. But once you get in this regime above 10 gigahertz, you increasingly see that FETs dominate. FETs appear in applications as high as 100 gigahertz and beyond. So this is now a regime in which bipolar technologies simply are not able to perform. These are typically above the F over T of available bipolar transistors. The principal advantage of FETs below 4 gigahertz is noise figure, for one, although there are copious applications for both FETs and bipolars below 10 gigahertz. So below 10 gigahertz, you will see bipolar and FET technologies appear, with the particular application being the thing that decides between them. Here's some information about FET technology families, a very brief discussion of a complicated topic. There are these things known as metal oxide semiconductor FETs, known as MOSFETs. These are typically used in RF applications at UHF and below, and you may or may not be aware of things called LD MOS, which is a type of MOSFET, which are used in some RF applications. A different material family consists of MESFETs, MES-FETs. This includes things like gallium arsenide FETs, gallium nitride FETs, and silicon carbide FETs. We also have the HEMT family, the high electron mobility transistor family. These are heterojunction devices, again referring to some details about how the transistor is manufactured. These are analogous to HBTs, where HBTs is a more complicated way to put together a bipolar transistor. Here's one type of HEMT that appears quite often. Another type is a pseudomorphic HEMT. These appear increasingly common as LNAs in wireless applications, and also lattice-matched variants of all this heterojunction technology. So there are many, many different ways to put together a FET transistor, or a transistor that behaves according to FET principles, but these are not going to be dramatic differences for us. What we need to know is how to bias it and its S parameters. If we can figure out that much, then the materials technology is not likely to enter into the design. It may enter into the design selection process. Yet another FET variant is the modulation doped FET, or the MODFET. And I should also include, for completeness here, the junction FET, or the JFET. This is actually the first FET that was commonly used in RF applications, and it still appears in many applications. So there are a few very well-known JFET transistor types that keep appearing over and over again in designs, even though that transistor was conceived many decades ago. So one final slide here. I keep pointing out this issue that we will most commonly consider common emitter for BJT amplifiers and common source for FET amplifiers, but they're certainly not the only choices. And here from the textbook, I'm showing you some other choices. This is just one possible way of looking at it. But for your information here, common collector configuration for BJTs, you take the output from the emitter. We refer to this as an emitter follower. And the analogous configuration for a FET, which I already pointed out, was you take the output from the source, so we call it a source follower. And the key feature of these two things is they have very low output impedance. This makes these things very good as current sources. So for example, these appear as line drivers or cable drivers in certain applications. The remaining configuration for BJT is known as common base. So the input is the emitter, the output is the collector, and the base is in common between the two. The analogous FET configuration is known as common gate, and the feature of these is very low input impedance and relatively low gain. So for example, one application for this is in LNAs at VHF and UHF, but again, not the only way to do it, just a common solution. So everything we're going to talk about in future lectures really applies more or less equally. This particular selection of input and outputs doesn't really change the way we bias the transistor. It changes the S parameters, and it changes the features that we have, the input and output impedance, the achievable gain, and those things. So we're going to concentrate on common emitter and common source, but again, not much different to use these approaches. This concludes this lecture on transistor fundamentals.